component list, methane, ethane and propane. Okay, boleh cuba buat tak? Sekarang saya bagi seminit atau 2 minit. Kelas, boleh cuba buat? Masukkan dulu add the component list. Boleh ya?
Boleh, Doktor.
Okay, cuba masukkan, saya bagi 2 minit sekejap je kan. Sebab you all pun dah buat presentation hari tu. So, basic saya rasa tak ada masalah kot Okay, we try to do it. Okay, give you 2 minutes. Okay, so we have methane. Okay, and then next component, ethane. Okay, and then you have propane. Okay, so all the green already. Semua dah siap sampai sini? Okay, class, have you done until here?
Dah.
Okay. Okay, so the next step, as usual, fluid package. So this time you are asked to use PR, the Penn Robinson. Okay, oh sorry. So the PR. Okay, and then you have green. Okay, next one we go to simulation. Okay, so the first step, you have a streamline. Okay, double click stream and then go to composition. Okay, so this time we are using mole of mass. Class, is it mole of mass? From the question, boleh refer pada slide notes Is it mole or mass fraction?
Mole.
Okay, so kalau kita tengok, okay, you are given with mass fraction Okay, so kita ada mass fraction and then nanti kita akan masukkan 25 degree C and also 20 bar. Okay, on the stream. And also the flow rate, 100 kmol per hour. Okay, let's go back to the ICs. Okay, and then you have mass fraction. Okay, change the basis to mass. Okay, and then fill up the mass fraction. So method is 0.5. Okay, and then the next one you have 18. Okay, 0.3, and the last one is 0.2. So make sure the total is 1, then you click OK. Okay, then the next part they ask you for unknown temperature, so we go to condition. Okay, and then fill up the temperature. Okay, 25 degree. Okay, and then you have 20 bar. Pressure. Okay, and then kilomole per hour. It is a molar flow rate 100 kilomole per hour. Okay, it is okay the green color. Okay, and then we close the window and then so you nampak stream dah jadi dark blue Okay, the next one you type for the equipment. The name is expander. So this is the symbol of expander. So you drag, sorry. Okay, drag the expander. So of course we have an expander and then we have the output. Okay, then the next part is to connect the stream. You have 1, and then you have outlet 2. Okay, energy. Okay, non-duty. Okay, so berapa dia punya efficiency tadi? Efficiency is 30%. Okay, 30%. So you just edit here, I add isentropic efficiency, polytropic tu biarkan okay, 30% and then enter. Okay, so you close dulu and then sorry. Okay, and then for stream 2, what is the information for stream 2 that we have? Okay, kita cuma ada T out as 5 bar. Okay, calculate the T out. Okay, that is the question. Okay, so we try to put 5 bar, the pressure. Okay, all green. So vapor phase 1. So it means that the output condition adalah phase dia adalah vapor. So 1. And then so automatically it will calculate for you the temperature as a negative 5.585. Okay. So dia ada lain sikit lah daripada jawapan dia adalah 562. Lebih kurang Okay. Okay, so that is all about the exercise 5. Okay. Okay. Okay, the next one, okay, the last exercise. Okay, as is exercise 6. So if I share the screen, okay, let's look into exercise 6 question. Okay, this is exercise 6 question. Can you see my screen? Okay, maybe you boleh, saya bagi you 2 minit untuk baca exercise 6 before we start with the HYSYS. Okay, so in exercise 6, okay, this time we use the heater. Okay, so the question is simulate a heater using the following information and then calculate the Q required to heat stream to a saturated vapor at 140 kilopascal. Okay, use PRSB as a fluid package. Okay, so kita ni lebih kurang macam heat exchanger Okay, basically you dah ada overview what you are going to have in your HYSYS. Okay, so kita ada stream, input stream, and then kita ada heater and kita ada output stream. So all the information including the temperature, pressure and also flow rate were already stated here, both for input and also output of the heater. Okay, you are given also the mole fraction and then these are all the component list which include the benzene, propylene, propane and also cumene. Okay, so you have a few questions here. So the first one, what is the V over F value of the input stream? Second one, what is the outlet temperature? Okay, and then calculate the heat duty. Okay, the next one is what is the flow rate of the output? And last one is what is the mole fraction of the output? Will it be the same or it is different? Okay, so we are going to start back with the HYSYS. Okay. Okay, boleh nampak Okay. So component list, we have 4 components. Okay. Okay, boleh masukkan dulu komponen untuk saya. Benzene, propylene, propane and cumin. Okay, maybe 1 minute. We do very quickly. Okay, class, have you done? Cuba untuk masukkan juga dia punya fluid package We are using PRSV. Class, have you done?
Done.
Okay. So I will do very quickly. Benzene. Okay, and I have propylene. Okay, propane. Propane. And last one is cumin. Okay, fluid package PRSV. Okay, then go to simulation. You have the input stream. Okay, so you fill up all the information starting from the composition. So as referring to the question, it is a mole fraction. 0.5 for benzene. Okay, and then propane and propane. 0.015. 0.015. Okay, and then last one is cumin. 0.47. So is 1. Okay. Okay, and then go to temperature, which is under condition. So it is given that the temperature is 25 degree. Pressure in kilopascal is 175. Okay, and then the molar flow rate 200 kilomole per hour. Okay. So we done with the input stream. Okay, so automatically we will know what is the V over F value. Sebab ini yang dia tanya V over F value is 0, so it means it is in a liquid phase. Is that right?
Yes.
Okay, then next one we need the heater. So we have heater. Okay, put heater here. Then kita ada. Okay. Okay, feed stream we have 1. We have 2. Maybe kita okay, 1. Okay. Unknown delta P. Do we know any delta P? Okay, dia tak ada bagi delta P pressure drop tak ada bagi. Okay, the next part is, okay, we leave it this first. Okay, so kita ada output stream. Output stream, what is given in the question, kita cuma ada V over F value and also pressure. Okay, so kita ada V over F value is 1. Okay, do we know the temperature? No, we don't know. We need to find it. Okay, what else they give you? Okay, the pressure is 175. Okay, so molar flow rate is 200. Okay. Then how about the mole fraction? Mole fraction, composition. Okay, kalau you tengok untuk string tu tak ada perubahan masih sama. 0.5, 0.015 and then 0.015 for propane, both for propane and propene. And cumin also maintain 0.47 Okay. Okay. So ini solve Okay, so finish about exercise 6. Okay. So the next part I'm going to show you. Okay, so we are going to have a reactor lab. So kalau soalan ni ada dalam Moodle dalam week 4. Boleh tengok nanti untuk week 4 Okay, so I start to share first. Okay, so have a look into the question. Okay, I give you 5 minutes to understand the question. Okay, so you cuba baca dulu untuk 5 minutes. Kaz, can we start now?
Can, Doctor.
Okay. Okay, so this is the conversion reactor and phase separator. Okay, later on in lab 4, 5, 6 and 7, kita akan tengok juga untuk plug flow reactor, the recycle stream, distillation column. Okay, so ini adalah salah satu contoh reactor because conversion reactor operation will not be the same as PFR reactor. Okay, so for this one, okay, conversion reactor and phase separator, it means that in this lab we are going to combine. Okay, we are going to have two equipments. That is a reactor, the conversion reactor, and also the separator. Okay, so the objective is to install and converge on a conversion reactor. The next one is to simulate a process involving reaction and also separation. Okay. If you see, this question is actually to produce the toluene, okay, from the N-heptane. But the reaction itself, N-heptane, okay, we have only one reactant here. Okay, so the product is the toluene and also hydrogen. Okay, toluene is produced from N-heptane by hydrogenation over a Cr2O3 catalyst absorbed on Al2O3. Okay. Even though there is a catalyst here, but since we are using the conversion reactor, the catalyst will not take part in the simulation. Okay, untuk conversion reactor memang catalyst kita takkan take part dalam simulation. But if you have a PFR reactor, okay, we have to include the information of the catalyst, okay, such as the void fraction. Okay, but the properties of the catalyst we do not put into the HYSYS. Okay, that one later on. Dalam PFR nanti kita akan tengok contoh macam mana you nak include the catalyst properties. Okay, sorry, the catalyst info. Okay, so we proceed with the conversion reactor. So we did not include the catalyst. Okay, N-heptane at the pressure of 8 bar is heated from 65 degree Fahrenheit to 800 Fahrenheit in a heater. Okay, you are given molar flow rate 100 pound mole per hour. Okay, the stream is fed to a catalytic reactor that operates isothermally and converts 15% of N-heptane to toluene. So it means that originally you have the N-heptane. Okay, so before the reaction happen to convert to toluene, this N-heptane need to heated up. So you need the heater. So kalau kita tengok dia punya soalan ni, saya cuba drag. Okay, so overall this is what you are going to have. Okay, so you have the toluene, you have the N-heptane in the input stream. So before kita ada sini adalah conversion reactor. So before the stream is fed into the reactor, you need to heat up the stream, the N-heptane. So you need a heater here, E100. Okay. So you need to heat up from 65 Fahrenheit to 800 in a heater. Okay, so you have to heat up first. The temperature 65 degree Fahrenheit to 800 Fahrenheit. Okay, we have the molar flow rate 100 pound mole per hour. Okay, and then after you heat up, then only you fed to the catalytic reactor. Baru masuk sini untuk menghasilkan 15% of conversion to toluene. Okay. Okay, and then it's stated here, the stream is fed to catalytic reactor that operates isothermally. Isothermally means what? It means that whatever the temperature here, okay, at stream 2 will be the same as stream 3. Okay, the temperature will be the same sebab dia isothermal. And since it is isothermal, so we have to supply the energy to the reactor. So sebab tu kita ada Q2 dekat sini. Okay, but even though we supply heat here, we don't know whether it is supply. Supply tu maksudnya kita tak tahu sama ada dia adalah endo or exo. But later on in simulation, we finally will know whether it is exo or endo by looking at the negative or positive sign of value. Okay, then what else? Okay, the effluent is cooled to 68 Fahrenheit and fed into flash separator to remove all the hydrogen from the liquid system. Okay, once you have here in stream 3, sebenarnya ada stream 4 dekat sini juga dekat sini. Tapi kita hide. Okay, nanti kita tengoklah kenapa kita hide. Okay, untuk stream 3 ni, okay, what we will have here is that we will have toluene, of course. Okay, that is the product, but only 50% is converted. Okay, and then the remaining 85% of N-heptane is still here in stream 3 together with the hydrogen. Okay, so kita hanya nak toluene saja kan, so kita kena remove dia. Okay, remove hydrogen, okay, daripada stream. Okay, and then before you do the separation, you need to cool down to 68 Fahrenheit and fed into flash separator to remove all the hydrogen in the liquid stream. Okay, so finally, this is a vapor stream in stream 6 and stream 7 is a liquid. So in stream 7, we don't want any hydrogen here. Because if hydrogen is here, we need a very low temperature to liquefy the hydrogen. So we nanti kita akan akan perlukan more energy, so will cost the higher cost. Okay, so sebab tu kita kalau sebolehnya kita tak nak hydrogen in liquid stream, so kita nak push dekat atas semua keluar hydrogen di upper stream, di stream 6. Okay, so now what is the question? Okay, next, sorry, ada kat sini. Then add a condenser at the outlet stream of the reactor and use a phase separator to separate toluene from excess N-heptane. Use SRK as a property package. Okay, use adjust operation to achieve the goal and optimize the separation process. Okay. Okay, so this is the gambaran lah yang you akan nampak dalam you punya HISIS. Okay, so how to start? Because ini adalah conversion reactor, so dia setting dia berbeza sedikit lah dengan cara yang kita buat sebelum ni. We have component list, that one masih sama. Next part is the full package, also the same. And then the third part, usually we go straight away to simulation, right? But since we have reactor, we will have to go to the reactor setting first. Then only we can go to the simulation part. Okay, let's start with this. Untuk soalan ni, you boleh refer kepada Moodle dalam week 4. Okay. Sambil tu saya share screen. Okay, so this is the HISIS that we are going to look into. Okay, so component list. How many component we have? 3. Is that right, class?
Yes.
Okay, so add. So we do it together. You cuba buat juga. Okay, masukkan dulu tiga tu, N-heptane, toluene and also hydrogen. Ini step yang biasa, so by right you dah boleh buat. Masukkan dulu dan masukkan hingga fluid package. Kita dalam ni kita hanya guna one fluid package saja, which is SRK. Okay, I give you 3 minutes untuk masukkan. Okay, we have pen. Next we have toluene. Hydrogen. Okay, so settle the first part. Go to flow package. Add the SRK. Okay. Okay, until this part so far okay? Ini senang saja kan? Okay. So I hope that all of you have reached this stage until flow package. Have you all done?
Yeah. Yes, Doctor.
Okay. So as usual, okay. Usually after we have completed component list and flow package, we go straight away to simulation, right? But this time since we have a reactor, so we go to the reaction part. Ni sebelah kiri So you just click. Double click and then kita akan nampak new one dekat sini reaction. Just double click reaction and then you have a interface yang macam component list tadi Okay, done?
Done.
Okay, then next click add. Okay, bila you click add tadi, okay, dia akan keluar interface macam ni. Okay. Are you following?
Yes.
Okay, and then next add reaction. Ni dekat bawah ni add reaction. Okay. When you click the add reaction, kita akan ada pop up the small window here. Okay, so kita ada reactant source, high cis, expand property. Ini tak perlu sentuh. Yang concern adalah yang 5 ni Okay, we have conversion, equilibrium, heterogeneous, catalytic, kinetic, and also simple rate. So for our case, this is a conversion reactor. So we choose the conversion. Click the conversion. Okay, just want to inform you. Okay, basically the conversion reaction in the real world it does not exist. Okay, dia sebenarnya this is just a method adopted by the high cis to simplify things. Okay, because yang wujud sebenarnya yang type of reactor yang wujud adalah contoh CSTR, PFR, BASH, itu adalah the real name ataupun condition yang wujud dalam industri tapi conversion ni sebenarnya tak wujud, dia macam dummy lah. Okay, conversion ni oh sorry sekejap connection loss. Okay, so in high cis we assume everything is perfectly mixed. Okay, okay, and then so the conversion reactor is actually a dummy type of reactor that exists in high cis. Okay, tapi kalau contoh you click kinetic, it means that it is a actual representation. It will calculate for us if the volume is too large ataupun the yield will be very low. Okay, so kalau contoh kita target, kalau you click kinetic ni because our conversion is 15%, right? So kalau you click kinetic ni, dia akan ambil kira semula size reactor. So you takkan dapat lah 15% conversion in exact value. Okay, so for this case kita choose conversion. So you choose conversion and then you add reaction. Okay, choose conversion, add reaction. Okay, once you add the reaction, kita akan appear dekat sini active reaction. Okay, active reaction, reaction 1, so maknanya hanya ada satu saja reactant. Okay, and then type conversion. Configured ni maksudnya dia belum, kita belum detailkan dia lagi. Kejap lagi kita tengok once kita dah configured, kita akan ada tanda tick. Okay. Okay. So far okay, boleh follow sampai sini?
Boleh.
Okay, next part. You can see active reaction here, reaction 1. You double click reaction 1. Oh sorry, close dulu. Okay. Okay, again I repeat. Okay, the next part is tadi yang window tadi you close. Okay, and then double click reaction 1. So dia akan pop up this window. Okay. Boleh dapat?
Dapat.
Okay. So what is important here in the reaction, because we have to inform the ICs what is our reaction which involve the component and together with the stoichiometric coefficient. Stoichiometric coefficient ni daripada equation tadi lah. Okay. So let's start with the component first. Okay. So you just pilih saja, ni ada drop down button. Okay, kita ada N-heptane, toluene dan juga hydrogen. Okay, you masukkan salah satu. Starting from the reactant N-heptane. Okay, so once you click N-heptane, dia akan automatically keluar mole weight. Okay, molecular weight. Okay, stoichiometric coefficient empty. Okay, biarkan dulu. Okay, next yang ada adalah produk toluene, also with molecular weight. And last one is the hydrogen. Okay, so semua molecular weight is given Okay. So sistem dekat sini tulis not ready. Maknanya you punya information masih tak cukup lah. Okay, have you done class?
Yeah.
Okay. So now if you notice dekat bawah ni kita ada balance error 0. Okay. You have to make sure that the total of the balance error must be always 0. Balance 0 means dia calculate daripada stoichiometric coefficient. Okay, so for stoichiometric coefficient we have to insert it ourselves. It is actually depends on the chemical equation yang tadi tu. So kalau kita tengok chemical equation tadi, okay. So kalau you ada notes you boleh refer. The equation is C7H16 1 mole. Okay, 1 mole of 1 mole of N-heptane, okay, will produce of 1 mole of toluene plus 4 mole of hydrogen. So maksudnya dia punya stoichiometry adalah 1 untuk N-heptane, toluene juga adalah 1, hydrogen adalah 4. Okay. Kita tengok dekat sini. Okay, kepada siapa yang tak buka lagi. Ini Okay, ni So you have, this is a chemical equation. So kalau you tengok dia punya balance equation, 1 mole of N-heptane produce to 1 mole of toluene plus 4 mole of hydrogen. So maksudnya sekarang you have to make sure that this equation is balanced, then only you can fill out the stoichiometric coefficient in the HYSYS. Kalau equation tu tak balance memang akan salah lah, nanti dekat total balance nanti akan salah nanti dekat sini Okay. Nanti dekat balance error ni dia akan dapat salah. Okay. Dia jawapan kat sini mesti 0 lah. Okay, contoh. N-heptane is the reactant. So dia adalah 1. But it is a reactant. So you put negative 1. Is that right? Bila belajar dulu CPP. Is that right class? Negative 1. Stoichiometry. Class, is it right? Negative 1. Why negative? Because it is a reactant. Class, are you following?
Yes, doktor.
Okay, negative means for reactant so negative 1. Okay, so bila you masuk negative 1, you nampak balance error jadi negative 100. So dia tak balance lah. Okay, next toluene also 1, but this time toluene is a product, so it is a positive 1. So I just put 1 ataupun positive 1. Ni understood positive lah. Okay, and then last, okay, so bertukar lagi, negative 8. And then last one, hydrogen is 4, so it is a product also, so it is positive. So I purposely put 4. Then enter. So bila you enter, you nampak balance error goes back to 0. So it means that your balance error is correct. Okay? So far okay? Class, so far okay?
Yes, doktor. Okay.
Okay. Okay, the next part, okay, untuk reaction ni dia banyak setting dulu sebelum masuk simulation. Okay, and then base component. Okay, you have to remember that for base component usually dia akan pilih limiting reactant. Okay, but now since our question, the reaction only have one reactant, so automatically dia pilih N-heptene. But kalau you ada 2 reactant, so you have to decide and know which component become limiting, which component become excess. It is your job. HiSys takkan pilih untuk you. You kena decide sendiri. Okay. But this one, as I mentioned just now, since we have only one reactant, so dia dah automatically choose N-heptene. Okay. Okay, how about reaction phase? Okay, reaction phase, if you click the drop down here, kita ada overall, kita ada vapor phase, liquid phase, aqueous and also combined liquid. Okay, usually kalau you tak tahu at the beginning biasa kalau macam you dapat project ke, kita buat DP nanti, if you are not sure, you can put overall. But later on, when we do the simulation, once you know the phase, you have to go back to this screen and then change the phase. Are you following, class?
Yes.
Okay. Okay, so for now, I don't know what is the phase, so I just put overall. Overall means dia combine liquid, kalau ada liquid pun dia boleh read, kalau ada gas phase pun dia boleh read, ataupun vapor phase ataupun aqueous phase pun dia boleh read. Okay. So maksudnya kalau phase sudah jumpa apa-apa phase sekalipun dia boleh read so I click overall. Okay, CO, C1 and C2. Okay, this is actually the value of the conversion. Okay, and then so kalau you tengok equation ni, dia macam untoin sikit kan equation dia. So dia adalah conversion as a function of temperature. C0 plus C1 T plus C2 T squared. Okay, CO, C1 and C2 actually representing the N-heptane, toluene, okay, N-heptane and also hydrogen. Okay, the C0, what is the C0 value? C0 is the conversion. Okay, C0 adalah N-heptane tadi, berapa persen dia punya ni? 15%, right? So 15% is student selalu confused you nak 15% sebab you selalu understood it is a 15/100, so you put 0.15. It is wrong Actually you akan masukkan 15 macam ni saja. Okay, 15. You takkan masukkan 0.15. You terus masukkan 15. Kalau ada 20, you masukkan 20. Jangan masuk 0.2. Is it right? Are you following, class?
Yes.
Okay. Okay, and then enter. Okay, so ready maksudnya tadi bila you dah masukkan conversion baru dia boleh read lah, because it's a conversion reactor. Okay, for C1 and C2 we do not know the value. Okay, so we just leave it empty. Okay, and then you see that it is a converge. Okay, so far okay? Class, so far okay?
Okay, doktor.
Okay, so saya close window ni Okay. So now, bila you close window, you akan nampak dekat sini, not attached to FE, FP. FP is fluid package. Because tadi kita dah set dia adalah SRK, but the reactor yang you create tadi tak attach, masih belum attach pada SRK. So how to attach? Okay, you click ni, add to FP, add to float package. Okay, okay, add to float package. So tadi kita dah declare dia ada SRK. So kita hanya ada ini sajalah. If let's say you have more than one basis, kita ada PR, kita ada macam-macam lagi lah. Okay, kalau macam tu you kena select lah which one is applied to the reactor. Okay class, boleh Kalau you ada more than one basis, you kena choose lah yang mana yang sesuai untuk reactor. Yang you dah choose untuk reactor. But this one, since we have only one basis SRK, so I just choose basis 1 and then I click add set to fluid package. Okay, I repeat. Okay, since we have only one basis here, so I choose basis 1 and then I click add set to fluid package. Okay, so basis 1, NC equivalent to 3. Aku masuk NC sama dengan 3 tu. NC 3 maknanya number of component list equivalent to 3. Betul lah tadi kita ada N-heptane, toluene and also hydrogen. So 3 number of component list 3, and then this one shows that we apply the SRK. So I click the add set to fluid package. Okay, bila you click itu baru you nampak dekat sini ready. Okay, so it means that reaction tadi set 1 is green on already, maknanya complete lah, converge. So far okay class? Agak berat sikit banyak lagi kena setting Ni baru reactor belum DC, belum lagi plug flow reactor Okay class, you nak break dulu ke macam mana? Boleh break dulu? Ni belum masuk simulation lagi baru nak masuk ni. Can we have a break? 15 minutes?
Boleh doktor.
Okay, 15 minutes sebab so kita reaction kita dah settle. So next part after the break kita akan masuk simulation Okay, so we come back at 9:45. Okay, thank you. Okay, for the simulation, okay, I'm going to share this video, okay, and then we try to do it together, okay. So while playing this video, I'm going to stop in the middle, okay, part by part, okay, to make sure that all of you can follow. Okay, so we do it together until we finish until the separation part. Okay, class, boleh?
Boleh, Doktor.
Okay, so I'm going to start now. Simulation. Now, we bring in this frame. Okay, we double click on this frame. We have to specify the composition, and the mole fraction in here is okay, so for the mole fraction, it is not given in the questions, but we can assume that by looking at the mole, okay, only n heptane exists at the beginning, okay, untuk stream 1 ya. So sebab tu untuk n heptane kita akan assume dia adalah 1, okay, 100%, while toluene and hydrogen at the beginning are 0 sebab dia tak wujud dalam dia belum produce lagi in stream 1, okay. Because n heptane is the only fraction, the only compound, so we put it in 1. Okay, so these are all 0, the rest. So this is 1, is okay. Then after that we go to conditions. Vapor phase fraction we do not know, we don't put it in there. The temperature is 65 degrees Fahrenheit. And then 8 bar. The molar flow rate is 100 pound mole per hour. Change this, pound mole per hour. So we are okay now. Okay. Then we have to heat it from 65 degrees Fahrenheit to 800 degrees Fahrenheit. So at this point, n heptane is in liquid form. So the reaction takes place in vapor phase. It seems that way lah because it has been heated. So we increase the temperature. But before that, you have to use a heater. So this is our heater. You have to use it this here, tapi this time kita guna heater dulu, later kita boleh replace. Now we bring in stream number 2. Let's connect this. This is 1, outlet is 2. We have to have energy. So the energy is Q100. So unknown delta P, you know you have to specify your pressure drop lah. So I will say, I don't know, 0.5 volt because this is quite large. 0.5 bar. Good Okay, untuk pressure drop ni, okay kelas, so far boleh follow boleh buat dekat ISIS? Kelas, boleh buat dekat ISIS? Anyone? Boleh respon?
Boleh madam, tapi saya lambat sikit.
Lambat
Saya
sikit
tertinggal sikit.
Lambat sikit macam mana tu?
Macam bawa setting untuk temperature pressure seperti tu.
Okay, saya boleh tunggu 2-3 minit. Okay. So you masukkan temperature, pressure pada input stream tadi. Okay, and then composition dah masuk kan? Okay, lepas masuk composition, then you masukkan under condition which include temperature, pressure and also flow rate. Okay, kalau nak minta saya tunggu, you cakap beritahu saya sebab kita akan buat sama-sama sampai habis Kita ada lebih kurang lagi 50 minit lagi. Okay. Sorry, 1 jam 10 minit lagi. Okay. Okay, so once you dah masukkan temperature, pressure and also flow rate at stream 1, you drag the heater. Okay, because you want to heat up the temperature from 65 Fahrenheit to 800 Fahrenheit. So dia adalah sangat-sangat a big difference. So of course 800 Fahrenheit tu adalah dalam vapor phase already. Okay. And then for delta P, as I mentioned in the previous class, okay, ataupun saya bagi tahu semula lah in case ada yang lupa. Usually kita akan delta P is not given actually in this question, but we can assume the normal estimation you can estimate. It is from 0.1 to 0.5 bar. Okay, boleh catat boleh jot down. Okay, normal estimation of the pressure drop for any for the equipment. Okay, for the heater and cooler biasanya antara 0.1 to 0.5 bar. Specific for heater and cooler. Okay, so kalau you choose 0.5 bar, it means that dia dah sangat-sangat besar lah, which is equivalent to 50 kilopascal. Itu yang the largest estimation lah yang you boleh buat untuk heater ataupun cooler. Okay, so macam case ni dia dah set pada, dia estimate the pressure to be the highest pressure drop, which is 50 kilopascal ataupun 0.5 bar. Okay, this is a good estimation Ingat nanti dalam untuk design nanti you kena ingat untuk heater and cooler usually you estimate from 0.1 until 0.5 bar maximum. Okay, ataupun 10 kilopascal hingga 50 kilopascal. Okay. Okay, class, can I proceed? Class, boleh Tadi siapa tadi dah settle ke? Dah key in semua temperature, pressure and flow rate?
Dah.
Dah Okay, saya sambung semula.
Number is between 10 to 0.5 is a good estimation. And after that, at the stream 2, we have to estimate the temperature that is 800. Estimate, we have to calculate. We have to put in 800 Fahrenheit, which is 426.7 degrees C.
Okay, because just now the target is to increase from 65 to 800 Fahrenheit. So sebenarnya temperature ni you boleh terus masukkan lah 800 Fahrenheit tadi Okay, and this is equivalent to 426.7 degrees C. Okay.
So we are okay. So we know this is in vapor phase. Yeah. So once we know this vapor phase, I would like to change the phase of the reaction it evolved. So I'll just go here to properties. I just double click on my reaction.
Okay, the purpose what we do is that remember yang tadi waktu phase tu saya pilih overall. Is it right, class? Tadi masa phase tadi saya pilih overall instead of specifying whether it is liquid, vapor or gas phase.
Yes, sir.
Okay, so now once you dah tahu daripada stream 1 dengan stream 2 dia adalah stream 2 adalah vapor phase, so you boleh edit semula. So how you do is that you go back to the property tadi dalam simulation you go back to the properties and then you go back to the reaction. Okay, kita akan tengok macam mana dia ubah balik edit yang phase tu.
Then I'll change the reaction phase. We have to put in 800. It evolved. So I'll just go here to properties. I just double click on my reaction. Then I'll change the reaction phase here. I will change it to vapor phase because I know everything is in vapor. from the simulation just now. So we are okay. We want to be precise.
Okay kelas, boleh follow untuk ini?
Boleh doktor.
Okay so semua dah buat ke? Dah tukar ke kepada vapor phase dalam HISIS? Okay. Okay, so after we edit this, then we can go back to the simulation part.
And we want to put in all the details in here. Okay, now let's go back to our simulation. So we are okay now. So this is then we fit this one into a rectum. Then you have to type it here lah. Type it conversion. But this is a conversion rectum. Okay. On the first one, you just type in conversion, it will go. It will come up. So I'll just drop the rectum here. Now the conversion rectum typically will have two output streams, so you have to bring in the streams lah. You have to bring in the streams.
Okay, so far sampai sini okay? Boleh jumpa tak conversion stream, conversion rector tu kat mana?
Boleh.
Okay, make sure you dah drag conversion rector dan juga two output stream Kenapa two output stream? Because you tahu the conversion of n heptane is not 100%. So of course kita akan ada 15% of toluene converted. Okay. N heptane converted to toluene, and then also the remaining unreacted of the N heptane, which is 85%, will come out juga. Okay, so kita akan ada dua stream kat situ lah. Okay.
And we want this reaction to be isothermal process. So what we do, we know we have to either supply or extract heat from here. We do not know at this point whether this is endothermic or exothermic, but it does not really matter. Okay, so you go in here and you bring this, just bring that, it will complete for you. Now,
okay, as I mentioned just now, okay, in the reaction setting tadi, awal-awal tadi, okay, the purpose we put the heat stream here because kita tak tahu heat tu supply ataupun absorb. Because we still do not know whether the reaction is exo or endo. So we just put it, simply put here because nanti kita akan tahulah melalui value of Q, heat tu sama ada dia negatif ataupun positif. So daripada situ kita akan tahu dia adalah endo or exo. Okay class, are you following? Class, are you following?
Yes, doktor.
Okay, so saya proceed.
who wants me to wait? Anybody wants me to wait? All right, I'll wait. Yeah.
For stream two, the pressure is how much?
Because we have specified at the heater, the pressure drop is 0.5. So this one becomes 7.5 lah. Yeah.
0.5 tu.
0.5 dekat you punya pressure drop. Pressure drop, I estimate that one lah. Sebab rasa macam besar this one.
0.5. Oh, okay.
0.5 bar.
Bar?
Yeah, 0.5 bar. It's 50 kilopascal. Okay.
Okay class, just want to mention to you because tadi kita dah ada pressure right, yang input pressure dekat stream 1. Tapi since kita ada masukkan value pressure drop as 0.5 bar tadi, so of course at stream 2 akan ada reduction of pressure lah because of the pressure drop. Okay, so pressure at P1 and P2 will be different due to the pressure drop. So of course pressure at 2 will be lower than pressure at stream 1. Okay.
Okay now, we are okay now? Okay, let's connect this. So the stream is stream 2, vapor outlet 3, liquid outlet 4. And we have energy option Q101 lah. Okay, and then because this is a reactor, it says here requires a reaction set. So once it requires a reaction set, we are going to recall that reaction set. This one feed package is already defined as this is one, okay? So we go to reaction. So this is the reaction set. So if you have a lot of reactions, because you have a lot of reactors, so you have to be careful on in choosing your reactor. So this is set 1, okay? And set 1 is attached to reaction 1, and everything is based on stoichiometric. We can also put it in conversion percent, doesn't really matter, because either one is okay, because we already specify how much is converted. Then we view the reaction. If you want to confirm that is the reaction that that has been attached to the reactor, so this is what it is. So it's correct. But
okay kelas, yang ni sebenarnya sebab tadi dia punya instruction adalah connect to reaction set. So tadi at the beginning we have already do the setting for reactor. So now how you want the high Cs to connect with the reaction yang you dah set mula-mula tu. Jadi macam mana nak connect? Okay, saya undur sikit video ni. Okay, so from here, so connect with the reaction set. So what you do is that you go to the reactor part dekat sini Okay, you click here dan baru dia akan keluar lah pop-up yang tadi Okay, so saya play balik yang ni
So we go to reaction. So this is the reaction set. So if you have a lot of reactions, because you have a lot of reactors, so you have to be careful on in choosing your reactor. So this.
Okay, untuk set ni disebabkan kita hanya ada satu set saja reactor yang you set the earlier part, so hanya satu sajalah. But if let's say later in your project, kalau you ada more than one set, you kena be very careful. Make sure set reaction yang you choose tu mesti sama dengan reaction yang sebelah ni tadi Nanti saya tunjuk contoh.
This is set 1. Okay. And set 1 is attached to reaction 1.
Okay, ni maksudnya kalau set 1 tadi kepada reaction 1 sebab you boleh ada banyak set reaction dan juga reaction sendiri tu pun boleh ada reaction 1, 2 and 3. Okay, jadi kalau contoh ni hanya ada satu setting dan juga satu reaction saja. Okay, so senanglah set 1 dengan reaction 1. Tapi kalau you ada more than one reaction, you pun kena hati-hati untuk pilih. Make sure you punya pairing tu kena sama. Okay, contoh yang ni set 1 kepada reaction 1 And then tadi kita dah base kepada stoichiometry, so sebab tu kita klik pada stoichiometry. Kalau you nak pilih conversion pun no problem sebab kita dah set 15% tadi Tapi based on this exercise kita proceed sajalah dengan stoichiometry Dan yang ni semua yang you dah set tadi bawah ni stoichiometry input negative 1 dengan 4, okay, balance error 0. Ni semua yang setting yang you dah buat earlier So kita recall balik lah sebab kita nak dia connect.